Okay, I think we can begin. And today we continue studying different kinds of regression models. And now it's time to discuss so-called mixed effects models. And actually, the first thing that I want to discuss is the problem that we are trying to solve. Let me assume that I have the following problem. Let us return to something simple like a t-test, and let us discuss the following possible experiment. Assume that we have some study that is devoted to studying difference in, for example, length of a sentence for people from different countries or different towns or with different backgrounds. So assume that we have something like this. We have several informants. And for each informant, we know, for example, from which city they are. So we have variable city. Like, for example, it is a hometown of a particular informant. And for each informant, for example, we ask them to write or to okay, let us assume that we're just getting some written text from these informants. So we have a text. And this text consists of sentences. And so we have, for each text, we have lengths of sentences, an array of lengths of sentences. So we have city, and assume that this city can be either Moscow or St. Petersburg, just for simplicity. And my question is it true that people in Moscow use shorter sentences than people in St. Petersburg? So this is my research settings, and I want to answer this question. How will you proceed? Which statistical tools will you use in this case? Mm-hmm. So, what do you think? I have one answer in my private messages, but I hope that there are more than one answer. What do you think? How will you compare this length of sentences for people from Moscow and for people from St. Petersburg? And how would you answer this question? I have another answer. So other options? Anybody else? So the third answer, I want more. Okay, so most of the answers that I have mentions t-test. And this is, in fact, what we are thinking about when we want to compare two series of numbers to two samples. So we want to use two sample t-test, and this is fine. There was one suggestion about chi-squared test, but in this case, we are comparing something like length. So we have a numeric variable, and we want to compare averages between two numeric variables, or better say, between numeric variables in two groups. And so this is exactly a two sample t-test. But I want to discuss it further. Let us assume that I have my table in the following form. So note that for each informant, I have a text, and this text contains several sentences. And so for each text, I have several numbers here. So my table can look like the following thing. We have informant, and we have city, and we have sentence length. And I have something like the following. I have informant AAB from city Moscow, and the first sentence of their text is 34, for example, characters. And I have the same informant from the same city, of course, and another sentence which is of length 109. And I have something like this. And then I have another informant from Moscow with sentence length 74, sorry. And I have another informant from St. Petersburg, and there's sentence length like this. And so on. So my data looks like in this table. So in this case, one row of this table is one sentence. So in this case, one observation is one sample. Then basically, what will you do with your t-test? How will you apply two sample t-test to this kind of data? Note that when we apply a t-test, we have two series of numbers. If we have two sample t-test, then we just prepare two series of numbers, two sets of numbers, and we feed these two samples into t-test, and then it gives us some answer like we have significant difference between these two samples, or we don't have significant difference. So how would you apply t-test to this data? Which numbers will you feed to your t-test?
Why can't we take results of Moscow citizens and St. Petersburg citizens separately and compare them?
Mm-hmm. So which numbers exactly will you feed to your t-test when you look at this table? Just
I will take first four results as,
So
I don't
this
know,
number,
as one part.
this number. So you have this number, this number, this number, this number. You feed it as a first sample to your t-test, and these numbers as a second sample, right? Okay. Everybody agree? Are there any other suggestions? So we can try. We can try to use to find significance in averages in average differences between this first set and another set. Are there any objections about this procedure? What do you think? What we are interested in, let me recall that what we are interested in is this question. Is it true that people in Moscow use shorter sentences than people in St. Petersburg? And so our answer, if it is correct, should be generalized. It should be possible for us to generalize this answer to the whole population. And when we speak about population, we think that the population is like all citizens of Moscow and all citizens of St. Petersburg. There will be influence of certain speakers, yes. In fact, let us think about this table. If I just use these numbers as my numbers that I use in t-test, then I think about it in the following way, that if I repeat this experiment, I will take the same informants, but I will ask them to produce different texts. So the reproduction of my experiment, if I use these numbers here, is just to use the same informants, but generate new texts. Why I say this in this way? Let us consider an extreme example. Let me consider an example when I have only one informant from Moscow and one informant in St. Petersburg. Let me assume that Imagine experiment when we have one informant in St. Petersburg and one informant in Moscow. And both informants created rather large texts. Their text contains a lot of sentences. And we have something like this. We have AAB Moscow, then we have AAB Moscow. For example, something like this. And we have another informant, BXY, from St. Petersburg with texts like 51, okay, 151, 123, 125. Assume that I have the data like this, like in this table. And if I just feed these numbers and these numbers to t-test, then most probably my t-test will say that I have significant difference between this set of numbers and this set of numbers. Just because these numbers are too large than these numbers when I compare their difference with their variance. But if I think about the data generation process for this sample of data, I see that what we are comparing here, if I compare these numbers with these numbers, do I compare people of Moscow with people of St. Petersburg, citizens of Moscow with citizens of St. Petersburg? Can I, if I see that there is difference between these groups of numbers, can I generalize my conclusion to the whole cities? I can't. Just because I have only one individual here and one individual here. So we see that in this case, if I just use t-test, just apply t-test to this kind of data, if I try to interpret the results of this t-test as a comparison between Moscow and St. Petersburg, I will get wrong results. Just, okay, statistically, these results are in the sense, okay, but I cannot interpret them as difference between two cities. I can interpret them as difference between this particular person from Moscow and this particular person from St. Petersburg. Do you see the effect here? So when you do any kind of statistical testing, you have to think about your data collection process or data generation process. And you have to think about the settings of your test. If we return back to the beginning of the course, we discussed that if you do a t-test, you imagine that, for example, you have two populations and you take your numbers, your samples from these populations, and you compare your populations. And when we discussed how we get our data, we said that these sampling procedures should be just sampling, just random sampling from the corresponding population. And if I use this data, then if I want my if I want this number to be an appropriate numbers that allow me to use t-test to answer the question that I'm interested in, what kind of experiment should I plan? So we see that if I do this experiment, when I get several numbers from each participant, this experiment do not correspond to the settings of the t-test. At least if I want in my t-test to compare citizens of Moscow with citizens of St. Petersburg. How should I change my experiment? For example, if I can change experiment, how should I change my experiment to address this issue? So I want these numbers to be samplings from the population, and my population is. Can you get more information? Yes, but what will I do with this information? We can find the mean sentence length for every speaker, and after that compare cities. The number of speakers from every city should be equal and rather big. Yes, Anastasia actually is correct. Actually, we can consider different ways how to overcome this issue. If we are interested in difference between cities, we can do one thing. We have to consider as an observation not a particular sentence from particular speaker, but the speaker itself. So we have to consider the speaker as our observation. And we can do it in different ways. For example, we can just pass from this table. We can find average for each speaker. So we have average here. We have average here. And we have average here. And then consider a new data frame for which for each speaker, for each informant, we will have one observation, one number, and then compare these averaged numbers. In this case, our experiment corresponds to the idea of t-test, because in this case, our population is just all citizens of both cities, and for each citizen, we have a value like what is the average the average sentence length of this citizen, and then we compare this average of these averages, and this is correct plan. Another way is just to get different citizens and just ask them to create a text with one sentence. This is also possible. But anyway, if we want to compare cities, we have to be sure that our populations in our experiment is a population of a city and not a population of all possible sentences in texts of a particular persons. So one possible solution is, in fact, average sentence length by informants. And switch to one informant, one observation. And in fact, in this simple model, this can be a good and possible way to do it. But this is not the only possible way to do it. Why not average by cities? Actually, if I do this thing, so if I find average by cities, then I will get just two numbers. But if I want to understand, do we see any statistically significant difference between these two numbers, I need to get some information about variance of these numbers. So I have to understand how citizens are different between each other. So I need a series of numbers here and a series of numbers here. Of course, when I perform t-test, I will find average of these averages. And this average of these averages, if actually this average of these averages will be close to the actual average over all the city, but we need this variance information. Okay. So this is one of the possible solutions. This solution is not perfect. For example, because we can consider different informants, and from one informant we have a lot of data. For example, one informant generated a long text with a lot of number of sentences, and another informant generated just a very short text with small number of sentences. And when we do this averaging, we forget about these aspects of our data. So we remove some part of our information. And actually, people use this kind of averaging, this kind of summarization, but it is also possible to consider it in a bit different way. So another option. Consider random effect model. What does it mean? Assume that I have the following two-step data generation process. I have a city, and in this city I have citizens. So we have citizens, and for each citizen we have an average length of the sentences that they generate. So we have some numeric value like m. This is Moscow, and the same picture for St. Petersburg. And mi is an average length of sentence generated by informant I. Then I pick my data generation process is the following. I pick random informant from, for example, from Moscow. So I pick random box here, and then I use this box to generate my sentences. So we can previously, when we discussed this models for population, that is just a large box with some balls in this box, and I sample from this box. We just sampled numbers from our population. But now I do a bit more complicated thing. I believe that in each of these boxes, I have, okay, let me draw a picture. I have one large box, and inside these large boxes, I have smaller boxes. And in these smaller boxes, I have balls. And I have numbers on these balls. And on each of these boxes, I have a label. So this is M1, for example, 23. And this is M2, for example, 45, and so on. So I have a box that consists of smaller boxes. And my data generation process is the following. I pick a random box, smaller box, from this large box. So data generation. First, pick small box from large box randomly. Then pick several balls from small box randomly with replacement for simplicity. Then repeat steps 1 and 2. Now this is my model. Do you see the analogy with the study that we discussed previously when we discussed our sentence length? So my small box is just one informant. I pick this small box, I pick a random informant, and then I generate some sentences from this informant. This is my picking of my balls, just sampling of some random numbers from this smaller box. And in this way, I generate my data. Okay, so this is just a kind of formalization of my experiment. Now, let me assume, again, for simplicity, assume that in each smaller box. Distribution of numbers is the same up to change of average. I mean that if I have some ball, sorry, if I have some box, I have this smaller box, for example, this one, and I can consider the distribution of numbers in this box. So, for example, I can just draw a histogram that corresponds to these numbers, and I assume that these histograms looks very similar to each other. They are different in their mean value, but in other aspects, they are just shifted version of one distribution. So I think that, for example, I have a first box where average is 23, and I have some distribution like this. I assume that it is just something that looks like a normal distribution, and this is distribution of numbers in box 1. And in box 2, where it is 45. So this is M1, and this is M2. It will be the same, more or less. I believe that when if I return to my example with informants, I say the following thing, that there are different people, and for each person there is some value of average sentence that this person produce. Of course, in real settings, this person can produce a little bit larger or a little bit smaller sentences, a little bit shorter or a little bit longer, but this deviance for different persons is more or less the same. Their average can be different, but the deviation from this average more or less the same. So this is my assumptions. Are there any questions about this part?
Why are you doing all of this? Like, what's the aim?
I just want to create some formal probabilistic model that then I can use as a version of regression model that will take into account this two-step data generation process. I just want to create a model that corresponds to the real process that generated my data. So this is why I need it. So does it look plausible for you? So if we replace these individuals, these informants with these boxes, and the process of generating text, we just replace by the process of getting some balls with numbers on them from a particular box. So this is just a simplified model. Okay. Okay. Now let me introduce the corresponding regression model. So I return to my initial data So I work currently with this table without averaging, with my original table. And now I do the following. Here, this sentence length is y. I create a dummy variable for city. And my initial regression model that corresponds just to t-test is like the following. Y equals to beta naught plus beta 1 times dummy variable that corresponds to city equals to Moscow. So this is initial regression model. Let us check that everybody are comfortable with this model. Let us discuss, for example, according to this model, how can we interpret the value of this coefficient beta naught? What is beta naught? What is beta naught according to this model? If I believe in this model, how can we interpret this value of beta naught? Why is this sentence length? I have only one variable, this dummy variable that equals to 1 if city equals to Moscow, and 0 if city is St. Petersburg. What can I say about this beta naught? Any ideas? We discussed this.
It is the average sentence length for people from St. Petersburg.
Correct. Average sentence length for people from everybody agree?
I didn't get the idea why people from St. Petersburg here.
Okay. Let us look at this. Let us look at this equation. If a particular person is from St. Petersburg, then the value of this dummy variable for this person is 0, because this variable is 1 if city is Moscow. Then for this person, y equals just to beta naught. So we understand that this y is a kind of average value because we consider a kind of model person, not a real person, but model person for whom this equation holds. But for this model average person, we see that the sentence length equals to beta naught if this person is from St. Petersburg, because in this case, this value is 0. Okay. Okay, what about beta 1? How to interpret beta 1? Mm-hmm. What about beta 1? So let me recall that in our experiment, we have several informants. And for each informant, we know their city. And for each informant, we asked to produce some text. And we split this text by sentences. And we counted this sentence length. This is, I just repeat these settings because I see that some people appeared only recently. So now we consider this regression model for this kind of data. And my question is, what is beta 1? How can we interpret this beta 1? If we believe in this model. So this variable, this thing is dummy variable that equals to 1 if city Moscow and 0 if city St. Petersburg. And we have no other cities in this experiment. So what is beta 1? So I have one answer. Anybody else? You can answer publicly, privately, by voice, by texts, any way you wish, but I want your answers.
It is kind of coefficient that that moves that line and maybe shows, I don't know.
Yes, it is a
some average of, I don't know what.
Average of what? Okay, let me consider a person from Moscow. What can you say about the average sentence length, about the average Y according to this model? If this person is from Moscow, what can I say about this variable?
It equals 1.
Yes, then what can I say about Y? Oh.
That equals b to 0 plus 1. I don't know, like that is another line.
Sorry, Y plus 1. Beta 0 plus what?
Plus b1.
Yes, beta 1, exactly. So for people from Moscow, average Y equals to sum of these two values. And so beta, let me write it. So beta naught plus beta 1 is an average sentence length for people from Moscow. So what can you say about this beta 1? And how can you interpret this beta 1 now? We have these people, we have these people. How can we interpret beta 1? So if this beta naught is an average for people from St. Petersburg, and this sum is an average for people from Moscow, how can we interpret this beta 1? So we see that this is just a difference between this average and this average. So beta 1 is just actually, this is just a difference between average sentence length in Moscow and in St. Petersburg. So actually, to use this regression is the same thing, more or less the same thing, as to perform two-sample t-test, because this beta 1 measures the difference between two groups, difference between averages between two groups. And if we see that this variable is significant, then it means that this difference is significant. And this is more or less the same thing as to do a two-sample t-test. Okay. Now this model actually ignores this information about informant. So in this model, we have the very same problem that we discussed previously when we discussed applying of t-test to these numbers. And to avoid this problem, we have to consider a different regression model, a regression model that corresponds to this two-step data generation procedure. And to do so, we have to add a so-called random effect into our model. We just say that actually this can be called mixed effect model. And in this case, we say that y equals to beta naught plus beta 1 times dummy that depends on a city. And plus some value u that depends on informant. So this u is called a random effect of informant. So we basically say something like the following. Our idea is the following, that this y determined not only by city, but also by some personal properties of a particular informant. So we add this variable here. And we believe that these values, this u of a particular informant, actually what is this? What is this thing? I say that for each informant, value beta naught plus u of this informant is okay. How to interpret it? I mean the following, that there are some difference between informants that are explained by this variable, by different city, but also there are some difference between informants just in one city. And we catch this difference between informants in this variable. In this case, for example, for people in Moscow, for each informant from Moscow, no, from St. Petersburg, this value, beta naught plus this u, is an average sentence length for this informant. So basically, if I return to this model, I just say that my, okay, if this is not Moscow but St. Petersburg, then my values of this u is just an difference between the average sentence length for a particular informant and average sentence length for the whole city. So we catch some differences between informants. And we assume that in random effects model, we assume that this variable is random. So basically, this equation corresponds to my data generation process that I discussed previously. I believe that for each informant, I just pick random average sentence length for this informant, and then from this informant, using this average sentence length, I generate several sentences, and then I get my data. Then I get my values of y. Note that the value of this variable is the same for the same informant. So this is like a correction for a particular informant. And in this case, I have a very simple model because I have only one variable here, and this variable is dummy variable. In more complex models, I can consider different variables. For example, I can add here age or gender or something else, like education, number of books that this particular person read, and so on. So I can create some more complex model. But if I have several data points from each informant, it can be a good idea to add this correction, this term, this random effect for this informant. Otherwise, it is possible that I will get results that are not correspond to the actual data generation process. Are there any questions so far? This is not very simple stuff. This is rather theoretical model, and I don't want to discuss in details how in this model we will find this beta naught and beta 1. The adding of this term makes it more difficult to explain how to find this beta naught and beta 1. The idea is to use the same maximum likelihood estimate, maximum likelihood method that we discussed previously when we discussed logistic regressions. But anyway, I don't want to go into details now. But the idea is that we can create this model, and this model is more correct. It corresponds to the reality in a better way than this model, because in this case we ignore this informant variable, and we believe that all these rows are generated from the whole population again. So basically, in this model, we just believe that we get a new informant in each row, and these informants are just not related to each other. But if we understand that we have the same informant that corresponds to several rows here, then we have to take into account this variable. So this is a new kind of models, and we will study them as well. Okay, other questions so far? Okay, let me then tell you about a research that we published in the previous year with, actually there are a lot of authors, including Mikhail Alexandrovich Daniel and Nina Rolandovna Dobrushina. And in this research, we used this mixed effects model, but not for just simple linear regression, but for logistic regression. And in this research, we had the following stuff. It was a research that was devoted to some dialect and non-dialect forms of different language features. And we have the following data. We have like there was several informants. So there was a question on how to find this U. This is done automatically. Actually, when you just feed this regression finds not only this beta naught and beta 1, but also these values of U that just gives the most the largest likelihood of your data. So this is done automatically. So let me return to my to the study. So we have several informants. And for each informant, we have their year of birth. And actually, in this research, when this data was collected, they created an oral corpus. So they recorded some oral speech, and in this speech, they considered different linguistic features. I don't know the details of these linguistic features, but I know that this linguistic feature can be either in dialect form or in normative form. So we have dialect or normative. Some linguistic features. And so, of course, it was like a natural speech. So each informant produced this just informal natural speech, and in this speech they can either use these features or not. For example, a particular word that can be in two forms, and then other authors of this paper counted how many times they used this feature and in which form. So for example, think about just a word that can be in two forms, and every time when this word is used, we can get either normative form or dialect form. And so for each informant, we have information about this these forms. So we basically have the following table. We have, for example, this is informant. And now let us consider just one linguistic feature. So every time when we see this linguistic feature, we add a row to this table. And we have year of birth. And we have this feature can be either dialect or normative. So we have variable dialect that can be either 0 or 1. So for example, we have the following table. Sorry. The same informant, the same year of birth. Something like this. So each row, one observation, is one use of some linguistic feature. For example, some word that can be particular word that can be in two forms. And one of our question was how fast these dialect forms disappear from the language. So it is natural to assume that people who are older are more tending to use these dialect forms than people who are younger. So we basically expect that we have something like this. If we draw a picture like here is year of birth, and here is proportion of dialect forms. We can expect something like this. If year of birth is small, then we have a lot of dialect forms here. And when this, we can believe that something like this holds. And then we wanted to check this statistically and to estimate how fast this disappearance of dialect forms and we wanted to check some other features of this process. And to do so, we used logistic regression, because you can think about this table and you can think about these values as just a binary outcome that can be either 0 or 1. And you can use logistic regression. But first, we just tried a simple logistic regression. We just used this as independent variable and this as dependent variable, and year of birth as independent variable. So there was something like log odds that dialect equals to 1. This is something like this. But in this case, we ignore the fact that we have different speakers, different informants. And when we tried to use this model, I found that I don't like how this model behaves. That, for example, this model thinks that the case when we have something like this, assume that we have a lot of usage of this feature here, and we have some point here which is close to this one, and we have some point here. So something like this. If this bold dots corresponds to the case when we have a lot of usage of this particular feature from a particular informant, then it is almost impossible if we believe in logistic model to see this picture, because in logistic model we assume that we have some curve that gives us probabilities, and if we have this curve, then if the value of this curve is somewhere here, it is almost impossible to get a point here. But if I add a new term, if I add a random effect of informant, then this new model becomes very natural. Actually, in this model, I believe in the following. I believe that each person has their own probability to produce dialect forms. And this probability is random. For a particular person, it is assigned randomly. But when it is assigned, it does not change. But how it is assigned depends on the year of birth of this particular person. So we believe that, for example, if this person is if their year of birth is smaller, then it means that probability for them to get the probability to generate dialect form should be on average larger than here. But again, we assume that for a particular person, we have their own probability, and it can be different even for persons who have a very similar year of birth, like this point and this point. And this model behaves very reasonably, and we used this model in this research. So basically, you can use these random effects in linear regression or in logistic regression, or even in some other forms of regression, generalized linear regressions as well. But this is out of the scope of our course. So this is what I wanted to discuss today. Any questions so far?
I have a rather theoretical question, like, does it work in like opposite way? I mean, can we predict something by the results? I mean, like if we have a table like we've seen before, like that, yes, and I don't know, and we get some information like that some informant with I don't know, like some average uses dialect forms. Can we predict which year of birth he is.
Yeah, I see your point. Well, yes, it is possible, but it is a little bit different problem. Let me think. If I know for
Like, does it has any predictionable, like, can we use this formula for some predictions? I mean,
yes, yes, we can, but this in this setting, we are trying to predict this variable. So we are trying to predict this column by using this column, by actually using these two columns. If we want to do it in the opposite way, I think we can, but I think that we have to use it in a different way. I think that if I want to do it, then I will average all informants. So, for example, I get 2/3 here, and okay, 2/3 here, and then I will just use something like linear regression just to predict these values by using the averages of these values. So I can transform my table into like a table A, B here, and here it will be proportion of dialect forms, and it will be, for example, 2/3, and so on. And then I can try to use linear regression or something like this. And in this linear regression, I will use this variable as my dependent variable, left-hand side variable, and this variable as independent. And
okay, and this prediction is gonna have some probability, isn't it? Or not? Or how it works? I mean, like,
well, basically all predictions that we have just gives us only some probabilistic answers, because we understand that the data is random. Actually, in this case, it can be a bit tricky, because, for example, if you have just assume that I have only one realization of a particular feature, and this realization is dialect. So I have, for example, for one informant here, I have just one row here. Then I will get here I will get 1 or 0. So either largest possible value or lowest possible value. Of course, I have to take into account that I just don't have enough data in this case to make this prediction. Basically, I think that if I have this problem, probably I have to use different kind of models, like something Bayesian, but I'm not sure. So yes, we have to take into account somehow the number of elements here, but what to do in this particular case if we want this kind of predictions. So it means that this model, in a good case, this model have to do the following thing. If it sees that you just don't have enough data, like you have only one realization, then it says, okay, my prediction is that year of birth either is from 0 to infinity, because I don't know. I don't have enough information. And the more data you have, the more realizations for a particular person you have, the better your prediction should be. So the narrower your confidence interval should be. It sounds like a problem for Bayesian approach, but I have to think a little bit about this particular problem.
that was just a theoretical.
Yes, I see. I see. So if, for example, if you know that for each informant you have a lot of data, then you can try to use just a linear regression in this kind of problem.
Mm-hmm.
And of course, when we discussed linear regressions, we said that for each coefficient, we don't have actually a correct numeric value. After we fitted these regressions, we don't have just one value for coefficient, but we have some estimate for this coefficient and some estimate for its variance. So basically, we have some confidence interval for your estimation.
Mm-hmm.
And it means that we also have only a confidence interval for predictions. Actually, when you do in ggplot, when you do, for example, linear models graphically, it draws something like, I think we discussed it, that if you have some points here and you do linear regression, then ggplot also draws you something like this. This is a belt, an area in which our prediction could lie. So in a sense, it says you that you don't have actual prediction for a particular point, but you have some region for which your prediction are plausible. So yes, it is some probabilistic answers in any case, but sometimes you can use them. Okay. Single u for many entries. No, here this value u depends on informant. So for each informant we have their own u, and so in a sense for each informant we adjust their average in such a way. Yes, basically we have a lot of straight lines. Correct. Basically, for each informant, we have their own straight line. But in this case, it is not very interesting because in this case, for a particular informant, we have this variable also fixed. But sometimes it is possible to consider different problems when this variable will not be related to a particular informant, but this variable will be related to something else. For example, assume that I study some, for example, results of some students in different schools. And let us assume that I have the following data. I have several schools. And I have several students in each school. And I have several tests for each student. And let us assume that I have some another variable. For example, I'm studying how internet connection quality affects study results. Assume that I have internet connection quality. Okay, internet connection quality. And probably I can consider some other variables, but I don't know. Okay, I can consider a model like y equals to beta naught plus beta 1 times internet connection quality. Plus beta 2 times u1 of student plus, sorry, not beta 2, but just plus U2 of school, something like this. So in this case, we have effects of student and effects of school, and then they can be added. So for a particular student, we take into account that there are some variability between students inside one school, and there are some variability between schools, and this and school can also affect the results of the student. So actually, these models can be much more complicated than we discussed so far. Okay. Okay, then let us make a 10 minutes break now, and then we return to discuss how to do this or this mixed effects models in R. So now we have to use a new library that can do this mixed effects models. So let me install it first. It doesn't work. So it's restarting. Okay, sorry. It restarts too long. Okay. Hopefully now it will work. I need a package that is called LME4. And so you have to install this package as well. And then use it. Let us download some data set. Doesn't work. Okay, just a second. I need to get this data from some other source. Okay, let me try to use different data set because I can't find the one that I want to discuss. Okay, let me use the following data set. This data set related to an experiment on perception of vowel reduction in Russian language. And we have two reaction times, duration of the vowel, some 4 months, and type of the vowel. And we have classification for vowels under stress, in the first syllable before the stressed one, and in the second syllable before the stressed one after the stressed syllable. And we are interested in how the first formant depends on the value of the second formant, and whether this relationship is different for different types of vowels. So we have this vowel type, and we have two formants that we are interested in, first formant and second formant. And so let me try to consider these regression models. Let me begin with just a simple model, linear model without any mixed effects. Like I'm interested in the relation between first and second formant. So first formant depends on the second formant. And this is our data. Okay, let me use tidyverse and let me use ggplot for visualizations. So we see that there is some relation between these two formants, but in this data set, we have all types of vowels mixed. So we don't see the difference between different types. And let us consider these results of our linear regression. And you see this negative value for this estimate. How can you interpret this negative value? So what does it mean if we think about this relation between first formant and second formant? I don't know what formants are. Garik Maros tried to explain it to me several times and without any success. So it seems that I'm hopeless in this aspect. But this is just two numeric features of some vowels. So what can you say about this negative coefficient? How can you interpret it? Anybody say something? Yeah, we see negative correlation between F1 and F2. So if F2 increased, then F1 decreased. And actually, we see this on this picture, this kind of negative relation. But let us draw here also some information about the type of vowel. So let me this variable vowel. Let me add it to my drawing. Okay. So let us look at this new picture. The picture when we have this, when we have different types colored with different colors. What can you say now? How do you think if I consider different types of vowels? If I pick a random vowel of a fixed type, what can you say about relation between first and second formant? If, for example, if I consider only vowels of type R capital. Yes, at least we see that before we created these colors, we clearly seen that there is negative relation because the picture looks like this one. But if we consider these groups separately, we see that this relation can be reversed. It is possible that here we have positive correlation or close to 0, I cannot say just by visual inspection of this graph. But anyway, it is possible. So let us try to use random effects model for this data set. Let us use this vowel type as a random effect. I'm basically not sure that it is a good idea. Probably we just have to add this vowel as just a collection of dummy variables as a so-called fixed effect. But I don't have a data frame that I wanted to discuss now. So let us just try to use the methods with this data set. So let us use this vowel as our random effect. To do so, I have to use a different library. Actually, a library that I already loaded, this LME form, this thing. And so did you manage to install it? Does it work? Mm-hmm.
If I have the same mistake as you have, I mean, like required package matrix, that
that's fine. That's fine.
that's okay.
Yeah, that's okay.
Okay.
This is not an error. This is just a warning that it was built under different version of R, and in most of cases this is okay. This is just an additional message that it loads another package that it needs, but it is not an error. That's fine. Okay. Then let us try to use the function LMER. And the way that we use this function is similar to this one, but we have new options. So we can look at this result. First of all, let us discuss this formula. In this formula, I say that I have a linear model, and my dependent variable is f1, and my independent variable first is f2, just like previously. And this thing represents my random effect for a vowel. So basically, if I write the same thing mathematically, it will be something like f1 equals to beta naught plus beta 1 f2 plus random effect of vowel. So for each value of vowel, we have its own value of this variable u. And our law is like this one. And this is the result of our fitting. And we have some information about our random effects. In this case, we have only one random effect that is this vowel random effect, and we have information about its variance. We just see how different values of this u we have here. And now we have this result for f2. It seems that we don't have information about p-values for a particular fixed effect in this formula, but at least it gives you some standard error. And you see that the standard error is close to the value of estimate. And you probably remember that confidence interval for the value is like this value and plus or minus 2 standard errors. So in this case, this coefficient is not significant. Actually, let me see how to find the corresponding p-value. Is it possible? Okay, there is another package, LMER test, that allows us to find the corresponding p-values. Then we can rerun the same thing. Yeah, and now we see that this F2 is not significant in our new settings. So it means that after we included this this random effect, we don't have any significant relation between F2 and F1. So if we consider this these vowels by groups, then we see that there is no significant significant correlation between F2 and F1. This is actually what we have seen on this graph. So if we allow different intercepts for different groups, then we see that this line can be more or less horizontal. And this is exactly the result that we have here. Okay. So in this, actually in these models, we can consider random effects of different kinds. If I put here just one, it means that I want to consider just some numeric value. So this is called random intercept. So I have model with different random intercepts, but it is also possible to consider different models. Let me write a function that will draw some graphs. Of our predictions. So it doesn't work. I don't know why. Okay. So this function predict allows us to find predictions by our model for the same data as we used. And now let us visualize it. This can be done using ggplot. Something like this. Okay, it doesn't work. Hmm. So we see these three straight lines that correspond to our three lines in our predictions. Note that these lines are parallel to each other. This is because we have the same slope. We have the same coefficient for F2. So these lines are different only in the value of this random effect. That's why this model is called random intercept model. So we say that for different groups, we have different intercepts, and we assume that this intercept is random. And now let us consider a different model specification For example, we can consider a case when different groups are different not in their intercept, but in their slope. So it is possible to consider different models with different slopes. Let us do it. So I have to put F2 here. Mhm. It says something that it doesn't work. This is, I don't know why, but these things sometimes happen. Anyway, let us try to look at the result. Okay, probably in this case, model has too much freedom, and so the result is not identifiable. Okay, let us try different specifications. No, the same thing here. Okay, probably it is not a good data set to show the effect that I wanted to show, but anyway, let us try to draw these graphs. So now I put here F2 instead of 1, and let me draw the corresponding graph. I have to put fit2 here. Okay, the results are very close to the previous one. Okay, just not the very best data set to demonstrate the features that I wanted to show you. Okay, let us discuss a little bit some theoretical features of our models. Let us consider the following data set. Let us assume that I have something like this. Assume that I have this data set, only 4 observations. And to begin with, can you tell me, without running any R code, or probably with running of this R code, what happens if I feed the following model? So this is just a simple linear model. I ignore informant column and just consider the relation between y and x. What can you say about values of beta naught and beta 1? Actually, this can be done without any computer tools, just by looking at this data frame. But if you want, you can use R to find these values. So the first question is find estimates for beta naught and beta 1. This is just a simple linear regression, so you can use just LM, linear model. Probably you can just guess beta naught and beta 1 by looking at the numbers. So beta naught is 4, or beta naught is 1. Beta 1 is 4. Okay, so there are a lot of different answers. Which one is correct? Okay. Okay. Look, we have these numbers here. So let us just try to draw the corresponding graph. So if we draw the graph, we see that our points lie on the same line. Actually, this is a perfect fit for linear regression. And we have to find parameters of this line. We have to find slope and intercept. And probably it is easier to find slope. The slope can be found in the following way. If we increase the value of x by 1, what is the increment of value of y? So for example, if we move from this point to this point, we increase x by 1, and y is also increased by 1. So the slope, which is beta 1, equals to 1. In fact, you can now just find the formula that relates these values of y with the values of x. You can see that this y is just, how can we find y if you know x? You just can see that y equals to x plus 4. It means that in this formula, beta 1 equals to 1, and beta naught is equals to 4. Okay. So this is just a linear model. Actually, we can try to do it in using LM. If I just do linear model. I get this result. It says that we have perfect fit, and that's fine. Now, let me consider a different model. I have this column informant. Let me add this column informant just like an ordinary categorical variable. So I can consider this column as just like a categorical a variable with categorical values, with 4 categorical values. Let me add this column to my regression model. Just without any things, without any random effects and so on, just as usual. So I just consider this thing. How do you think? What will be the result of this model? So let me return to my data. This data. You see that I have different informant for different observations. So for each informant, I have my own observation. And what can you say now if I just include this informant into this model? It means that I include a variable. Okay, basically I will include 3 dummy variables here that corresponds to different informants. What do you think? What we will see here with this model? Even better, let me just use this model. So before we proceed, let me consider this theoretical exercise. Let me consider the model for which y equals to beta naught plus beta 1 dummy variable informant b plus beta 2 dummy variable informant this model. Before I do this linear modeling with R, can you find all betas? For my data. So I have 4 possible informants, A, B, C, D, and I have this model. Note that I don't have X on the right-hand side at all. What can you say about the values of betas for this model? I tried to predict Y without using X, but using information about informant. How can I do it? Okay, actually you can do it without computer. Just look at this equation and look at our data. And say me what are appropriate values of beta 0, beta 1, beta 2, and beta 3. Anybody here? Any questions about this formula? In this model, we don't have X at all. So we don't have to take into account X or use X in any way in this model. In this model, Y does not depend on X at all.
So is it B, C, and D, and that's all?
I don't understand. We have informant, and this is categorical variables. A, B, C, D are just categories. It can be names. And I have these dummy variables that take values 1 or 0, depending on does this condition is satisfied. So, for example, for the second row of my table, I have the value of this variable equals to 1, value of this variable equals to 0, and value of this variable is equals to 0.
Okay, so what's the question?
The question is to find the values of beta, beta 0, beta 1, beta 2, beta 3. They are just numbers, such that this equation is satisfied for all rows of our data. Actually, in this case, you can do perfect fit. So in this case, you can just make your residuals to be 0. So you can make this equation to be satisfied perfectly for all rows. So, for example, let us consider the first row. How can you write your equation for the first row? So we have informant A, x1, y5. I want to okay. Let us put this information into my, into this equation. What will I have? So y equals to 5. Then I have beta naught plus what? One. Sarah, why 1?
I think 0 because this is not informant B. So informant A has
yes, we don't have
zeros.
dummy variable for condition informant equals to A. So for the first row, all values of these dummy variables equals to 0. So D informant B equals to 0. D informant C equals to 0. D informant D equals to 0. So, oh, sorry. Let me just increase the font size. Okay. So you see that if you put these zeros here in this formula, then you have just equation y equals to beta naught. And for the first row, y equals to 5. So beta naught equals to 5, right? So please find other betas in the same way. This is a simple exercise, but it is really important. Just a second. So I have one correct answer. So what can I say about beta 1, the coefficient for this dummy variable? To find this beta 1, we have to consider the second row of our table. So we see that we can put beta 0, beta naught 5, beta 1, 1, beta 2, 2, and beta 3, 3. And then our equation will be satisfied. So basically, what does it mean? It means that if I have this data for which each row has only one informant, if I know informant, then I can deduce y with absolute precision without any errors, even if I don't know x. So basically, this allows me to fit this model. Let us try to do it with R. Yeah, we see exactly the values that we found by hands. But it also means that if I include variable x, it will not change. It will not change. It will not give me any new information. Actually, it means that I cannot find from this kind of model, if I take into account this informant, I cannot get information about the relation between y and x. Let me try to put it in this way. Okay, it says something about these values, but it says that it cannot it cannot find the value of one of these dummy variables, and basically it says that the result is rather strange due to this NA. Actually, it means that in fact it cannot deduce the value of x, the value of coefficient for x correctly, because for any possible coefficient, we can adjust the result using this variable, because we can just specifying by specifying of these values of these betas, we can create any y as we wish, and it does not depend on other variables that we have in our data set. So that's why if we just use this informant variable as just like a regular fixed effect, so in this way, it just does not make sense. But if we add the same variable as random effect, we will get different result. Let me try it. Okay, no, it just doesn't want to do it. Yes, and it in a sense reasonable. Okay, it also doesn't work because it also doesn't make sense to consider a case when we have only one group for each observation, because we want to use this random effect if we have some grouping, like we discussed at the lecture. We have several rows for each informant, but if we have only one row for each informant, then it doesn't make sense. Okay. So I think that we are more or less out of time. Are there any questions? Okay.
Actually, I have a question. Sorry. Sarah has a question.
Yeah, yes. Okay. I just we can call them with any other names. This is just a convention to call the result of some linear models as fit, because the procedure of finding the coefficients of this model is called fitting sometimes. So the result is fit, but this is just a convention, and I just reuse the same variable many times if I don't need to show two models simultaneously. So just a naming, just a convention.
I have a question. So, is it possible to use several methods for our data? For example, for our experiment in our course paper, I know that it is bad to try to find something by some of the methods, but is there a case when it is okay?
Yeah, I think I get your question. Yes, in fact, it is recommended. At least in our course project, it is recommended to try to use different methods. And in fact, in science, it is also a good way if you have some data, and you try to use this data to make some conclusions, to say that you found that there is some kind of relation between your variables. And it is good if you can show that your conclusion, in a sense, does not depend on the method that you use. This is called robustness check. When you use a slightly different but reasonable ways to do your analysis, and you produce the same result. What is bad is when you try several methods and remove all the results that you that does not in agreement with your hypothesis, and only keep the results that is in agreement with your hypothesis. This is bad. But if you try different methods, for example, different model specifications, or different methods like regressions and some other modeling methods, and you consistently get the same result, or you get different results, but you can explain why these results are different, then this is perfectly okay. So in our course, you are encouraged to use different methods to look at the data and to try to understand the data generation process that created this data, to understand how you collected your data, how your experiment or your data collection works, and to try to find probably several reasonable methods that allows you to test your hypothesis. So this is perfectly fine. Yes.
Thank you.
Okay. Other questions? Okay, then that's all for today.
Thank you. Bye-bye.
Bye. See you in a
Thank
week.
you.